we've talked about feedback and tip imaging, let's move on to the broader question of how you can take the best possible image and how you can be on the lookout for artifacts in that image. You'll find that there'll be a lot of choices, and most of those choices will have some kind of advantage and disadvantage. Let's take a look at them now. As you prepare for an AFM session, you'll be choosing a cantilever of spring constant K. The lower the spring constant, the better the force resolution. The higher the spring constant, the greater range of forces you could apply to the sample. That cantilever will also have a frequency at which it likes to oscillate that is equal to the square root of the spring constant over the mass. I already mentioned this in lesson 2. Now I'd like to be more specific. That resonant frequency is usually denoted with a little naught as a subscript. That tells us that this is a particular frequency, the natural frequency, the frequency at which the cantilever likes to oscillate. The mass in the denominator, it is not the volumetric mass, meaning the density times the volume of the cantilever. Rather, it's an effective mass that accounts for the distribution of the mass along the length of the cantilever. We need to think about the dynamics of the cantilever because as we're imaging, we might be subject to going over steep and sudden changes of topography. So let's imagine that we have the cantilever in free space. We pluck it and we watch the oscillations go up and down. That function, as a function of time, looks like this, starting here and going back and forth like this. This is a cosine wave, and if we take this point here as the amplitude, let's call that d, as in the set point deflection. The y-axis will be this direction, and that will be z of t. For this equation, then, we've got z of t is equal to the deflection, set point deflection, times cosine of the resonant frequency times the time. If we wanted to find the time in the first half cycle of oscillation, meaning that we might know this position z, and we're looking for the corresponding time t, we would solve this equation for t. How do I do that? Well, I divide both sides by d, and I get z over d is equal to cos omega 0 t. Then I take the arc cosine of both sides, and I'm going to drop the t on the z just to make the equation simpler. I get omega 0 t. Then I divide both sides of the equation by omega 0, and I get t is equal to 1 over omega 0 times arc cosine of z over d. One thing I forgot to mention is that omega 0 is measured in radians per second as opposed to cycles per second. That's something to keep in mind should you ever use the equation in red. We'll use this equation in red in a couple of slides. When you sit down for your AFM session, one thing you should check on your microscope is how many pixels it's going to gather. And what I'm sketching here is a grid pattern. This is how an AFM collects data. It collects data in a grid of a certain number of points. This particular grid is 4 by 4, and so this very, very simple image would have 16 pixels to it. Well, you're not going to get very good resolution. A more typical size is 256 by 256. That is 65,536 points. That's a reasonable size for making a postcard or putting an image into a report. The file sizes are small, doesn't slow the instrument down too much, but of course it's not great resolution. If you want more resolution, you go up in the number of pixels, 512 by 512. That's 4 times as many pixels overall. File size will be 4 times bigger. It might take you longer to acquire the data, but on the other hand, you have better resolution for the same scan size. You'll also set your scan parameters during the beginning of your AFM session. You'll set the scan range, that is, how far do you want the scanner to move, and you'll be setting the scan frequency, that is, how many times per second do you want the scanner to cycle back and forth. You should know some vocabulary here. This is the fast scan direction. This is the slow scan direction, the way I drew the path of the tip there. You'll also set your force, set point force, which is essentially the deflection of the cantilever that the feedback loop is going to be holding constant. Let's pull these ideas together. We'll have a step, cantilever moving over it from left to right. This is a view down the long axis of the cantilever. And these 2 points are separated by a distance s, which is the smallest step, i.e. it is the range divided by the number of pixels. The height of this cliff is h, and our coordinate system is, this is the z-axis, this is the x-axis. In order for the image to be good, the time response of the feedback loop has to be less than the time it takes the cantilever to move vertically, cover that height, and that has to be less than the time it takes the cantilever to move horizontally 1 step over the range. Let's take these times one at a time. The time it takes the cantilever to do 1 scan step is s over the speed in the x direction. 1 step length is the range divided by the number of pixels. The speed in the x direction is the distance for 1 cycle, meaning back and forth across the fast scan direction, 2r, times the scan frequency, the number of cycles per second. The r's cancel, and we get 1 over the quantity, 2 number of pixels times the frequency. For the time it takes the cantilever to move vertically over that cliff from top to bottom, you remember a few slides ago we had this equation, z of t is equal to d, the set point deflection, times the cosine of the quantity resonant frequency times the time. I'm going to add the h subscript here to that time. So we solved that equation for time a few slides ago, and we came up with 1 over the resonant frequency. The arc cosine of the quantity z over d. Now, in this situation, we don't exactly have z, but we have the equivalent is it's the deflection minus the height of the cliff. So there we go. Now, pulling all these together and putting them back in the white equation on the lower left, what we get is that the feedback time response, which you control through the gain, must be less than 1 over omega 0, resonant frequency, arc cosine, set point deflection, minus the height of the feature divided by set point deflection. That in turn must be less than the time response to move one scan step horizontally, which is the inverse of twice the number of pixels times the scan frequency. So looking here at this final equation, we see that there's a lot in it. The feedback time is set by the gain. Here, the resonant frequency, that's from your choice of cantilever. The D's are your set point deflection. The H is the height of the features, that's your sample. P, how many pixels you have in your scan in one scan direction, and the frequency of the scan. So you remember in the feedback lesson I talked about always having to adjust your feedback gain, and now I hope you appreciate why. Now let's say you're getting some decent images, but you want to maintain your healthily skeptical attitude about artifacts. Your images are probably free of artifacts if, when you repeat the scan, the features don't change. When you change the direction of the scan, your features don't change. And when you change the frequency of the scan, your features don't change. As you just learned, you might have to change the feedback gain when you change the scan frequency. You should also make sure that your features scale appropriately. What I mean by that is if you have a 1 by 1 micron image and you have a feature that's this big, when you go to a 2 by 2 micron image, your feature should have half the dimensions. And finally, if you're unsure, you should rotate your sample. So here we have a sample. Features look like this. We rotate it by 90 degrees. The features should look like this. And both the relative position of the features should rotate. So this triangle is rotated by 90 degrees. And the orientation of the features should rotate by 90 degrees. Happy imaging!